Hello, good morning. My name is Panagiotis Katsaros. I'm associate professor in the School of Informatics, Aristotle University of Katsaros. And I'm going to give a short talk about forecasting and risk management in forest fires via Internet of Things technologies. It is a subject that I'm working on together with colleagues here in the School of Informatics for the last 3 years. Oh. Okay, so when we talk about firefighting, forest fires, the main priorities is first to find ways for the proper assessment of fire risk, to be able to immediately detect ignition spots so that firefighting forces can be notified, timely notified, to be able to continuously monitoring and predicting of the fire spread, I mean the direction and the strength of the fire, and to be able to timely and safely implement proactive evacuation of populations from threatened areas. So all these are main priorities, and we have various means to implement today. We have an increasing use of technologies, but the main means that are available in civil protection today are the use of hazard maps, the use of video radar surveillance systems, and more rarely the use of surveillance UAVs and drones. We consider that all of them are very useful, but we're going to introduce another technology which we believe is complementary to all of these. The limitations of the means that I mentioned in the previous slides are the following. First, the hazard maps refer to geographical compartments, and they do not offer geographically localized information for the microclimate condition in the forest area, which is very important for the way that fire develops. Another limitation is that the video and radar surveillance systems are very costly to deploy, especially in large forest areas, and they do not provide adequate data for the climate conditions to properly assess fire risks. And the third limitation is that surveillance UAV drone systems have high operating costs and a limited flight time window, so they cannot fully cover an area for 24 hours a day. We believe that they are very useful, but we believe to utilize them in a cost-efficient manner. And I'm going to explain what I mean by this. What we believe is that there is a need for low-cost solution that will complement the aforementioned means. And this low-cost solution can be provided by an Internet of Things system. I have included a few slides in order to introduce what exactly we mean the term Internet of Things. Internet of Things is an umbrella term that includes multiple different categories of systems, like, for example, wireless sensor networks, internet-connected wearables, low-power embedded systems, radio frequency identification-enabled tracking, use of mobile phones to interact with the real world for sensing, devices that connect via Bluetooth-enabled mobile phones to the internet, and so on. So you easily understand that the area of Internet of Things includes very heterogeneous systems. There are many cases that all these systems are interconnected in order to provide some function. So even the same Internet of Things systems can be very heterogeneous in terms of the technologies employed. But The main function of such a system is that the sensors collect and transmit data to be stored and processed in a cloud infrastructure. The purpose of the analysis of big sensor data is to extract useful values and to provide suggestions or decisions for a process, how to develop, how to control, or for a phenomenon, how to counter this phenomenon, and so on. It is true that there is no single architecture that will suit all categories of IoT systems that I presented the previous slide. And we have very diverse requirements which depend on the category of IoT system that we're talking about. But there are some main principles. So we can identify that an IoT system basically consists of the components that you see on the right. We have the devices that are deployed in the field. They may be personal, wearable, or embedded devices, which are used to accurately collect sensor data and enable actuation with secure communication. We have gateway devices. So the sensor devices are connected to gateway devices. These gateway devices, the main function is to convert messages obtained from sensor devices to internet protocols. So gateway devices provide access to the internet communication infrastructure. And the data are acquired and accumulated in the cloud infrastructure. And then we are able to perform analysis on the data in order to make predictions. We may use historical data analysis, or may even employ some real-time data analysis. And of course, in such a system, we also have open the possibility to connect various clients, like, for example, mobile devices, web information systems, which can provide insight into the trends, statistics, to follow a phenomenon, and perhaps to make timely decisions. There are various reasons why IoT systems are ubiquitous today. First of all, as we can see in this slide, the cost of sensors has decreased rapidly over the past few years. So today we can buy very cheap sensors, which are quite good in order to perform a certain function. Another fact is that the data transmission rates over time have been rapidly increased. You can see here that we can have data transmission with 1 gigabps and even higher. Whereas the data transmission prices have fallen over the time, the cost of communication is much cheaper today than it used to be a few years ago. And as a consequence of all this, we see that the number of connected devices in the internet has been increased over time. By 2020, it was estimated to be about 50 billion devices connected to the internet. Now, this slide presents how it is possible to integrate IoT telemetry and to use it for firefighting forest fires. First of all, we have IoT devices or nodes which acquire data from forest areas, which use low-cost sensors. The field data is sent periodically in cloud infrastructure via internet communication, as I showed you before. And we accumulate real-time and historical spatiotemporal data, which is available for various analyses. First, we are able to predict fire risk, for example, based on identified periods of intense drought and current weather conditions. It is very important to take into account both this. Second, we can detect ignition spot and predict the fire spread based on data like, for example, the wind direction and speed, if we have such data. So all these results of the analysis, I mean the prediction and the information from incident detection, are available for operations planning, proactive dispersion of civil protection units, and proactive evacuation plans of threatened areas. A very important communication technology that has wide adoption in the last few years is the long-range wide area net. This allows communication between IoT nodes or devices with a gateway device. You can see here the gateway device. And the LoRaWAN is a protocol which is a low-power protocol built on top of the LoRa radio modulation techniques. And it provides a communication range up to 4.8 kilometers. Of course, this depends on the geography, but these are the specifications. So we decided to invest on this kind of communication technology to develop our approach for forecasting and risk management of wildfires. In our system, which is called Maestro, and it is the result of a research and development project, first, I'm going to present the IoT node and device architecture. The node or device consists of two microcontroller boards. The small one that you see here, it is a Stival STR KT01 LoRa IoT tracker, which is an STM32 microcontroller, STM32 microcontroller unit, and it provides LoRa communication with the gateway. It also features GNSS circuits, which means that all the data are geolocated. And it also integrates a sensor for temperature and humidity. On the other hand, we also use a Nucleo microcontroller board, which allows connecting much more sensors, essential for our application. And these two boards are connected in a master-slave architecture. So the Stival microcontroller unit plays the role of the master, and the Nucleo plays the role of the slave. They are connected via the serial peripheral interface, which means that these two, they have full duplex synchronous communication. Now I'm going to say a few words for the software, especially the software for the Nucleo board. We have implemented a multi-threading program, which means that we have multiple threads which are scheduled by the FreeRTOS operating system. It's a real-time operating system which allows scheduling the running threads. And the program goes through these modes. So first, it is in a sleep mode, which means low power consumption. When the thread is awake, then we have the data acquisition from the sensors, and then we have the data dispatch, which means communication with the other microcontroller unit, which implements LoRa communication. I'm going to say a few words for the used sensors, but I wanted to clarify that we did not have experience from the use of sensors. Our main priority was to keep the development cost very low, because we want these devices to be very low-cost devices. But now we are at the stage of studying the sensitivity of the use sensors and maybe to replace some of them if we believe they are not adequate for our application. So we use a flame sensor, you can see here. We use a wind sensor, which measures the direction and the speed of the wind. This was the most expensive sensor. And we also use a smoke detector sensor. All these are connected to the nucleo board that you see here. For the power management, we have integrated solar panel and power management unit, which has a rechargeable battery. And here the challenge is to properly configure this circuit such that it will be possible to recharge the battery in periods that we would have sunshine. Now I'm going to say a few words for the data, how a few of the analysis that we have implemented. First, how we can estimate the risk of forest fire. There is a related research. For example, we have the Fosberg indicator, which we have implemented. You see the formula here, and the risk depends on the humidity coefficient and the wind speed. And here you see that the risk can be very high, the risk of fire, when we have Fosberg values between 38 and 50. Other indicators are the Kids biome indicator, which also takes into account drought measurements and average rainfall in an area. So this means that we need to combine and integrate data that are available from other sources, not only from our sensor nodes, and take them into account in estimating the risk. And there is also another indicator which is called Goodrich indicator. So all these different indicators can be used to estimate the risk of wildfire. But I have to clarify that the use of the sensor node is dual. So one of its role is to estimate the risk of forest fire, and the other role is to guide the civil protection forces in case of a fire incident. So this means that we have a different frequency of sending data when we don't have a fire incident. So the frequency is lower, but when there is an identified fire incident, the frequency is changing and we have more fresh data. Then the challenge is how to determine a fire incident. And this is a problem of sensor fusion that we are still working on. So we have a flame sensor and a smoke sensor. The first experiments showed that they were not the proper ones. We have replaced them. Now we are going to continue with other experiments. But I believe that the determination of a fire incident is not a matter of a single sensor measurement, but it should be a matter of a combination of multiple sensor measurements. The role of the UAV in case of a fire incident could be to notify and to take off a UAV in order to affirm that there is a true fire incident in the area. You can see here some screenshots of the dashboard. You can see here measurements of the wind speed, measurements of the humidity here, and here what you see on the right is the risk estimate based on the Fosberg indicator. So all this analysis is on real-time data. But as I mentioned before, we also have historical data analysis, and we also provide some graphs which show the trends, for example, of temperature, the trends of humidity, and so on. So the Maestro node or sensor device, you can see it on the left. We have the consortium company, which took care in order to package all these circuits and install them in a proper box to be easily placed in forest areas, like you see here on the right. We have sensor nodes placed in different heights. The experiments that we made in order to study the sensitivity of the different sensors. These were the first experiments on sensor sensitivity, and we have replaced the flame sensor with the smoke detector sensor, and we're going to repeat the experiments in the field. So this is the end of my presentation. I'm available for questions, if you have any questions. Yes, please.
What exactly does a flame sensor detect?
The flame sensor, as I said before, did not work very well, and the reason is that it always emitted a signal of flame, but it was not a real flame. It was the ray of the sun ray. So we want to have a less sensitive flame sensor, but its purpose is to detect flame in a distance of 3 to 4 meters from the sensor node. Another problem is the possibility these sensor nodes to be destroyed by a fire incident. But since they are low-cost sensor nodes, we do not really care for this because we believe that the data emitted until the time that the node is destroyed are valuable for firefighting. Now we continue research on this subject, especially the analysis, big data, because we know very well that these data are correlated because we have data from neighboring nodes and they are geolocated. So we have to develop methods for spatio-temporal data analysis that take into account possible correlations between neighboring nodes. This is a very interesting research. But the problem is that we need to find ways to test the credibility of these analyses, and we need to find the data from the real and the climate conditions at the time that these fires start. Any other question? And as I said before, we will consider this solution as complementary to other solutions. We believe that all of the solutions mentioned here are valuable. And we believe that especially the combination of these low-cost sensor nodes with surveillance, UAVs, or drones can be a very effective solution because we know on the one hand that it is not possible to fly UAVs 24 hours a day, but on the other hand, it may be very important when we have an identified incident by a sensor node to send a UAV there in order to affirm that a fire incident takes place or not.